Hello everyone, welcome to this channel. If you're new here, my name is Hasan. Let's begin our 8th part of the video series. This video will deal with the introduction of refraction, optical density, refractive index, laws of refraction, Snell's law, and some numerical related to the topic. I'll suggest you to watch all these videos on big screens such as computer or laptop, or maybe on smart TV at 1080p for best result, rather than going through these videos on smartphones, and also use a headphone. So let's begin the process of learning. Oh, but before that, let me share with you a beautiful quote. The beautiful thing about learning is that nobody can take it away from you. Now let's roll the intro. Okay, let's start our study on the topic of refraction. Again, I will tell you that take note of what I'm saying or what you see on the screen, and you'll see that all the topics are connected to each other. So as we move along, things will be becoming easier and easier. Okay, so it's an easy topic. Yeah, so let's get started. So let's start with the definition of refraction. What is refraction? Very easy. Refraction is one of the property of light. See, light has many property. One of the property of light is refraction. One of the property that we learned earlier for light was reflection, isn't it? Now the second property that we'll be learning is refraction. So that's clear. So refraction is one of the property of light. Now if you come into the definition part, then it says that refraction is the phenomena in which when light passes from one medium to another, it bends. Okay, so simply I can say that if this is one of the medium 1, and this is medium 2, okay, this is normal. So when light comes from medium 1 to medium 2, then we see that light bends. This phenomena of light bending when passing from one medium to another is known as refraction. But the important thing that you need to understand is the mediums should have different optical density. So medium 1 and medium 2, these two should have different optical density. Then only light will show this property of refraction. Okay, now what is optical density? I'll be discussing. Don't worry about that. First of all, look into this diagram and see that when we dip a pencil into a beaker or into a glass having water, then we see that the pencil looks bent. And this is a very common phenomena, and this is very practical. As a student, we have seen this. Okay, so this bending of pencil is due to the property of refraction of light, because ultimately when the light bends, that bending of light comes and enters our eye, as a result of which we know we see object, because light goes and hits the object, and that light reflects back and enters our eye. The same concept is followed here. The light goes but it bends, and that bent light enters our eyes, as a result of which we see the pencil to be bent. So you can see that the pencil looks bent because of refraction. So this is the concept and the definition of refraction. Now let's move on and understand what is optical density. So what is optical density? It is the measurement of refractive medium's ability to slow or delay the transmission of light. Now what does this actually mean? So let me draw and things will be clear. Suppose this is medium 1 and this is medium 2. Okay, this is the normal, and light comes and hits this medium surface, and then it enters and the light bends, okay, by the property of refraction. Now what does optical density actually do? Now optical density slows down the velocity of light travel. As you can see, it's written ability to slow or delay the transmission of light. So higher the optical density of a medium, slower the velocity of light in that medium. I think this is the easiest way in which I can explain. Now see, things will be clear. So optically denser medium, what does it actually mean? It means that light will travel slower in that medium with respect to other medium. Okay, look into this diagram. This light is traveling at velocity v1, and then after entering medium 2, it is moving with velocity v2. If v2 is smaller than v1, we can say, since the velocity has reduced in the medium 2, we can say that medium 2 is optically denser. Why? Because we can see light will travel slower with respect to other medium. I hope the concept is clear. Okay, now optically rarer medium means light will travel faster with respect to other medium. Now again, look into this diagram. Okay, things will be clear. In the earlier case, v2 was less than v1, and we said that the medium 2 is optically denser. Now let me rub this off. Now if I draw again, okay, this is the normal, this is medium 1, this is medium 2. Light comes and falls here, okay, and then it travels in this way. It bends, okay, away from the normal. We'll be explaining when it will go away from the normal, when it will move towards the normal. that will be coming later, so don't worry. So we said that the velocity here is v1 and velocity in medium 2 is v2. Now if v2 is greater than v1, we say that medium 2, since the velocity in the second medium is greater than the first medium, we say that medium 2 is optically rarer. I hope the concept of optically denser medium and optically rarer medium is now clear. Now it has nothing to do with the density that you have learned in mechanics in class 11 in hydrodynamics. Okay, that is, density is mass by volume. It has nothing to do with that. This is a different thing. Optically denser, optically rarer are different thing. It is how the light travels or how the velocity is affected that determines whether the medium is optically denser or optically rarer. Okay, I hope the concept is clear. If you haven't taken down the notes, then pause the video and take the notes. Now let's move on to our next concept, that is how to measure optical density. Okay, now let's see. Okay, now once you have understood what is optical density and what is optically denser medium and what is optical rarer medium, now let's understand how to measure optical density. Okay, the quantity that is used to measure optical density is known as refractive index, as I've written here, you can see, and the symbol for refractive index is mu. Okay, this one. So let's understand what is refractive index. Refractive index mathematical definition is given here. It says mu is equal to speed of light in air or vacuum divided by speed of light in the medium. We know that speed of light in air is denoted by c, that is speed of light 3 into 10 to the power 8 meter per second, and speed of light in the medium is denoted by v. Okay, so what is mu actually doing? So mu is actually comparing the speed of light in the medium with respect to speed of light in the air. So basically what we are doing in refractive index is that we are comparing the speed of light in the medium to the speed of light in air. Therefore we can see mu is given by this one, mu is equal to c by v. Now we know that c, the value of c is 3 into 10 to the power 8 meter per second, and this is the maximum value that the speed of light can have. Okay, that is in air or vacuum. Therefore you can say that the value of mu, since v is always less than c, therefore the value of mu will always be greater than 1. Okay, because if v is smaller than c, we can see that the value of mu will always be greater than 1. So for any medium, we can say that refractive index or mu is always greater than 1. The simple reason is that because the velocity of light in any other medium, leaving out air or vacuum, for any other medium the speed of light is always less than the speed of light in air or vacuum. Okay, I hope this much is clear. So once we have understood that the value of mu is always greater than 1, the next thing that you need to understand is greater the value of mu means smaller the value of v. See, we know that mu, let me rub this. So we know that mu is actually inversely proportional to velocity. So you can see the greater the value of mu means smaller the value of v, isn't it, from the equation of refractive index? Therefore the greater the value of mu means optically denser medium, because if this is greater, then v has to be smaller, and we know for optically denser medium the velocity is small. Greater the optical density of a medium, smaller will be the velocity of light in that medium. So if the velocity decreases, then what happens? The refractive index mu will increase. As a result, we can say that greater the value of mu means optically denser medium. Why? Because we can say greater the value of mu means smaller the speed of light. And since the speed of light is smaller, we can say that the medium is denser. So again, I'll wrap it off by saying that greater the value of mu means optically denser medium. I hope now you can understand that how refractive index is used to measure the optical density of a medium. So this is how we measure the optical density of the medium, and the term that is used to measure it is known as refractive index. Okay. Now let's understand some of the meaning linked with refractive index mu. Okay, let's understand what does mu is equal to 1.33 actually means. This mu is equal to 1.33 is actually the refractive index of water with respect to air. When nothing is given and simply mu is equal to 1.33 or 1.45, something is given, when nothing is given or mentioned, that means it is the refractive index of the material or the medium with respect to air. Okay, I hope this is clear. Now we know that mu is equal to c by v. Therefore we can say that mu, which is given as 1.33, is equal to c by v, or v is equal to c by 1.33. We brought the v on the left hand side. Therefore we can say that mu is equal to 1.33 for a medium means when light enters that medium, its velocity decreases by 1.33 times. So this is very important. So what does mu actually tells us? The first thing that we have understood, that mu gives us the information about whether the medium is optically denser or not. Okay, the greater the value of mu, greater is the optical density of that medium. Okay, so this is the first information that we get from mu. The second information that we get from mu is that, suppose it says that mu is equal to 2. Suppose, what does this actually means? Now mu means refractive index of a medium with respect to air. Okay, so this is the medium with respect to air. It says the value is 2. That means the velocity of light in that medium is 2 times smaller than the velocity of light in air. Okay, this is the second meaning of refractive index. I'll repeat again. If mu is equal to 1.75, this actually means that the velocity of light in that medium is 1.75 times smaller than the speed of light in air. I hope this is clear. It has to be smaller because the speed of light is maximum in air. That is the maximum. Okay, so this is very important. I'll highlight this with a different color. We can say that mu is equal to 1.33 for a medium means when light enters that medium, its velocity decreases by 1.33 times. And we know that since the velocity is decreasing, we say that that medium is optically denser medium with respect to air. Therefore, we can see that mu is greater than 1. We know that refractive index for denser medium is always greater than 1. And hence, we can say that velocity will absolutely decrease. I hope this much is clear. Once this is clear, we can look into the last concept related to refractive index, that is absolute refractive index. Now this is very easy. Just understand what does absolute refractive index actually means. The absolute refractive index actually means that we are finding the refractive index of the medium with respect to air. So very important, medium with respect to air. Whenever we are finding refractive index with respect to air, we say that kind of refractive index as absolute refractive index. Okay, and the value of mu is always greater than 1. You need to keep this thing in mind. They can ask you in MCQ. Okay, so this is all about the basic fundamental concept of refractive index. Now let's move on to our next concept. Okay, now we are ready to look into the laws of refraction. The first law of the first case says that it's very simple. Whenever light from a rarer medium enters into a denser medium, then light bends towards the normal. As you can see, it's written light bends towards the normal, and it's also shown by the diagram. Okay, see, the light is coming from the rarer medium, okay, optically rarer, and this second medium is optically denser. So whenever light enters from a rarer medium into optically denser medium, then light will bend towards the normal. Therefore, we can directly say that refractive index mu2 is greater than mu1. Why? Because mu2 is optically denser than medium 1. Okay, so this is the first case. Now the second case is just the opposite of the first case. That is, whenever light traveling from optically denser medium enter into rarer medium, that is optically rarer medium, then light bends away from the normal. Therefore, we can simply say that mu2 is greater than mu1, which signifies that mu2 is optically rarer than mu1. So as you can see in the diagram, the rays moves away from the normal when light enters from denser to rarer medium. So simple as that. The third case is very simple. Whenever light rays traveling from rarer medium enters into denser medium, or light from denser medium enter into rarer medium in such a way that it hits the surface normally. As you can see in the diagram, the ray of light is hitting the surface of the second medium normally. In that case, there will be no bending. Now it can be that the light is moving from rarer medium to denser medium or denser medium to rarer medium. It doesn't matter. If the light rays fall normal to the surface of the second medium, then there will be no bending. So this is the third case. Now the fourth point is that the incident, refracted and normal all lie in the same plane. The same concept that we have learnt in the laws of reflection, that is the incident ray, the reflected ray and the normal all lie in the same plane. Now in this case, in the part of refraction, the incident, the refracted and normal all will lie in the same plane. So simple as that. I have nothing to explain here. Now the last thing is principle of reversibility. Let me draw this and it will be simple. This is the normal. Okay. This is suppose medium 1 and this is medium 2. Now principle of reversibility says that, let me pick another color. Suppose this is the ray coming from medium 1 and entering into medium 2. Now this is mu1 and this is mu2. If mu1 is smaller than mu2, that means the second medium is optically denser medium. Therefore the rays will move towards the normal. isn't it? I hope this much is clear. Now the principle of reversibility says that if I reverse the path of light, like if I reverse it in this way, now the ray of light is moving in the opposite direction but following the same path, then we see that after refraction it follows the same path in the second medium. Okay, this is known as principle of reversibility. Okay, simple as that. I hope the concept of principle of reversibility is clear. So these are the laws of refraction. I hope this is clear. There's no complexity in it. Now let's move on to our next concept. Okay, now we have understood the laws of refraction, and we have also understood what is refractive index and what is its symbol. It is denoted by mu. We have also understood what is absolute refractive index, but how to represent this refractive index of the medium with respect to other medium, how to represent that. Now let's understand that. So refractive index of water is given as mu of water is equal to 1.33. Now, since I mentioned earlier that whenever refractive index of a medium is given and with respect to what is not given, like with respect to which medium is not given, simply it says that refractive index of water is 1.33. It actually means that it is the refractive index of water with respect to air. So the comparison is done with air when nothing is given. So that kind of refractive index is known as absolute refractive index. Okay, so the representation of that is, as you can see by the arrow, it is represented by refractive index of water with respect to air. So the refractive index of the medium is written on the right hand side. The medium with which we are comparing is given on the left hand side. For example, mu to 1. So mu to 1 means refractive index of 2, that is written on the right hand side with respect to 1. Now sometimes in some books you see that it's written in this way, that is refractive index of medium 2 with respect to 1. It can also be written as refractive index of 2 with respect to 1. So there are multiple ways of writing that, but doesn't matter. The refractive index of the material that we need to find out is always written on the right hand downward side. Okay, as you can see, it's right hand downward side, right hand downward side, right hand downward side. Okay, so this is how we need to represent the refractive index of the material with respect to other material. Okay, so as you can see, mu to 1 is refractive index of 2 with respect to 1. Now we know that refractive index of a medium, as you can see here, is inversely proportional to velocity. This concept has already been established earlier. If we use that concept, we can say from this that this is refractive index of water with respect to air is given by velocity in air divided by velocity in water. That is the velocity of light. So we can see from this that the refractive index of water is inversely proportional to velocity of light in water. So inversely proportional, that is following this concept. Okay, if we use that concept, then we can say that the first box that you can see, that refractive index of 2 with respect to 1 is v1 by v2, that is velocity of the light in medium 1, velocity of light in medium 2. Since we are finding the refractive index of medium 2, therefore its velocity should be inversely proportional. So you can see here it's inversely proportional, and v1 is the velocity with which we are comparing. Okay, now if you look into the second box, we'll be using the same concept, this concept, that is the refractive index is inversely proportional to velocity. Therefore we know that mu to 1 is v1 by v2 from the first box, isn't it? Now we know that refractive index of 2 should be inversely proportional to velocity in medium 2, and refractive index of 1 should be inversely proportional to velocity in medium 1. So we can say that if you look into the first box, that v1 by v2, so let me write it out, rub this. So v1 by v2 from the earlier box, if we take that v1 by v2, we can write this as mu2 by mu1, isn't it? From this concept, that is mu is inversely proportional to velocity. So you can see that mu is inversely proportional to velocity, mu is inversely proportional to velocity. So you got the second box, that mu2 by mu1 is equal to v1 by v2. Okay, now let me rub this off again. Now from these two boxes, we see v1 by v2 is mu2 1, and again v1 by v2 is mu2 by mu1. Therefore if we compare these first two boxes, then we can say that mu2 1 is equal to mu2 by mu1. Very important. Okay, this is our third box. So mu2 1 is equal to mu2 by mu1. So if they give you in the question that velocity of water is something, suppose x, and velocity of glass is suppose y. Now I haven't written anything on the left hand side, therefore it means that it is comparing with respect to air, isn't it? So this is the concept. Therefore mu w is equal to x and mu g is equal to y is given. Now they tell you to find out that what will be the refractive index of glass with respect to water. How to find out that? It's very simple. So this can be found out very easily, that is mu g divided by mu w. How? From this concept, because mu21 is equal to mu2 by mu1. Now mu g is refractive index of glass with respect to air and it's given as y, and the refractive index of water with respect to air is given as x. So you can easily find out the refractive index of glass with respect to water, or refractive index of water with respect to glass can be found out by mu w by mu g, where this is with respect to air, this is with respect to air, and you can find out. So this concept is very important. Okay, I hope the concept is clear. Now another part is remaining based on this formula, is that what is the relationship of this refractive index with respect to wavelength. Okay, now let's see that. We know that the velocity of light has a formula, c is equal to frequency multiplied by wavelength, that is nu into lambda. Okay, now one thing you need to understand about frequency is that frequency always remains constant in medium, to medium. So let me explain this with a diagram. Things will be easy. Suppose this is the ray of light coming from medium 1 and entering into medium 2. Okay, and it bends. It doesn't matter whether it's denser or rarer, it bends. Okay, so we say that frequency in medium 1 is equal to frequency in medium 2, that it remains constant even if the light rays move from medium 1 to medium 2 or medium 2 to medium 3. The frequency remains constant. Frequency only change, very important, frequency can only be changed from source. Frequency can be affected only by source. Okay, this is true for both light as well as sound wave. Okay, because both are waves. We'll be learning that in wave optics. Okay, it has been very good, nicely explained in the chapter of oscillation. Okay, if you have problem, then you can check that chapter in your book. So frequency can be affected only by source, not by the medium. This is very important. The only thing that is left is c with lambda. So if frequency is constant, we know that whenever light travels from one medium to another medium, then velocity changes, that is velocity, that is c changes. Therefore if c changes, then something has to change, that is lambda has to change, because frequency is constant. We just use the formula. We know that mu1 by mu2, since it is inversely proportional to velocity, so mu1 by mu2 is v2 by v1, and we know that v1 velocity is given by frequency into lambda. Now frequency, that is nu into lambda 1, because nu remains constant. Lambda 1 is the wavelength of the light in that medium 1. And for v2, we know that it is nu into lambda 2. Frequency remains constant, it doesn't change with medium to medium, as I've explained. And the wavelength in medium 2 is lambda 2. So frequency and frequency got cancelled. So we can say that mu1 by mu2 is lambda 2 by lambda 1. It's directly proportional to velocity. So if you just understand, let me write it here. If you just understand that mu2 by mu1 is equal to v1 by v2, if you just understand this, we know that lambda is directly proportional to velocity, so this can also be written as lambda 1 by lambda 2, isn't it? So simple as that. So let's see the last sentence here, that is the refractive index of water with respect to glass. It's given by refractive index of water divided by refractive index of glass, as I have explained earlier, and this is actually with respect to air, and this is also with respect to air. Okay, is equal to, since now we are equating this term with respect to velocity, therefore we know that refractive index and velocity are inversely proportional. Therefore these two are inversely proportional. So mu w by mu g is equal to vg by vw, which is again directly proportional to velocity, is lambda g by lambda w. I hope this concept is clear. The relationship are very important, because in NEET they will ask directly question from the relation. Okay, just put the relation, put the formula, and get the result. Remember one thing, that they will never ask question that can't be solved within 1 minute in NEET. So questions are easy and direct and formula based. So just understand the concept. If you have a good fundamental concept, then you can absolutely score 120 marks in NEET Physics. Okay, so this is all about the relationship of refractive index with wavelength. Now let's move on to our next concept. Okay, now we'll be looking into the concept of Snell's law. Snell's law was given by a Dutch astronomer and mathematician, and his actual name was Wilbrod Snell, in the year 1621. His law gives us a relationship between angle of incidence and angle of refraction. This is what his law actually suggests. Okay, now why this is important? Because in case of reflection, we have seen that there is a relationship between I and R, isn't it? That is, angle of incidence is equal to angle of reflection. Therefore, if we get the angle of incidence, we can easily find out the angle of reflection. Okay, so that was easy. The relationship was easy. But there was no such relationship between angle of incidence and angle of refraction in case of refraction of light. So if we know the angle of incidence, what will be the angle of refraction? In order to find out that, there has to be a relationship between I and R. This was unknown to us before Snell's law. There was no such relationship that could tell us that if angle of incidence is this much, then what will be the angle of refraction. They went on trying many such relationships, but every relationship went on falling down, and it was unable to satisfy the relationship between I and R. Therefore, I is not equal to R1, we can see, and there was no such relationship called I square is equal to R square or any of the thing. Finally, Snell's give us this relationship telling us that sine of I by sine of R is actually a constant, and I have written down the formula here, but before that, this was given by Snell. So let's look into that. We have seen that we have taken three cases here: case 1, case 2 and case 3. Now in case 1, the angle of incidence is I1. We got the respective angle of refraction as R1, as you can see here. Okay, for the second case, we have taken I2 as the angle of incidence. We got refraction as R2. For the third case, angle of incidence is I3 and we got angle of refraction as R3. So he said, according to Snell, he said that the relationship between angle of incidence and refraction is that sine of I by sine of R is equal to sine of I2 by sine of R2 for the second case, is equal to sine of I3 by sine of R3. This is the third case. The ratio of these are actually constant, and he said that this is constant. So whatever may be the angle of incidence doesn't matter. Sine of I divided by sine of R will be a constant value. One thing that should be kept in mind is that the medium pair should remain same. Okay, as you can see, for all the cases, that is case 1, case 2 and case 3, we have seen that we're changing the angle of incidence, and accordingly the angle of refraction is changing, but the thing that is remaining constant is the medium 1 and medium 2. As a result of which, he says that if this is satisfied, that is medium 1 and medium 2 is kept constant, then sine I1 by sine R1 is equal to sine I2 by sine R2 is equal to sine I3 by sine R3 will remain constant. That is, the ratio of the sines of angle of incidence and angle of refraction will be a constant, and this is actually known as Snell's law, as you can see in the screen. Okay, I hope this is clear now. So very easy. What does Snell's law actually do? Snell's law gives us relationship between angle of incidence and angle of refraction. Okay, now let's move on. Once we've understood sine I by sine R is constant, if you think a little earlier to this, we have learnt a concept where we said the ratio of something we have learnt is also a constant, isn't it? Now you'll see what is the magic. Okay, now let's move on. Now that constant that I'm talking about is that velocity in medium 1 divided by velocity in medium 2, that is v1 by v2 is equal to constant. Okay, this thing we have already learned while we were going through the concept of refractive index. And we said that refractive index, that is for a given medium, always remain constant. Okay, until and unless the pair of medium remains constant, then we can say v1 by v2 is always constant. Okay, from there we said that mu, that is the refractive index, is inversely proportional to velocity, and we found out this relationship, that is v1 by v2 is equal to mu2 by mu1 is constant. Okay, so this is easy. Now it was observed that now Snell said that sine I by sine R is a constant. Okay, this is a constant, and this again v1 by v2 is also a constant, mu2 by mu1 is also constant, and it was seen that actually this sine I by sine R is equal to v1 by v2 is equal to mu2 by mu1 is a constant, and there is a relationship between sine I by sine R, that is Snell's law, with refractive index as well as velocity. Okay, so this is the relationship between Snell's law and refractive index, that is sine I by sine R is equal to mu2 by mu1. Once we understand that there is a relationship between sine I by sine R is equal to mu2 by mu1 for a given pair of medium, this is very important. We can't change the medium. This has to be constant. If this is constant, we can say from this, it is very important, and this will help us to solve many MCQs. That is, if we cross multiply, okay, then we will get mu1 sin I is equal to mu2 sin R. Okay, so this relationship is very important. Now let me draw this so that it's easy for you. This is the normal. Now this is the angle of incidence I, and this is the angle of refraction R. This is medium 1 and this is medium 2. Okay, the relationship says that, very easy, that refractive index of medium 1, that is this one, refractive index of medium 1 multiplied sine of incidence that is happening in the medium 1, we multiply this two quantity, is equal to refractive index in medium 2, this one, and the sine angle that we are getting in the second medium. So this is actually in medium 1, this is also in medium 1, is equal to medium 2 multiplied by the quantity that we get in medium 2. Mu1 sin I is equal to mu2 sin R. Okay, this is how you need to remember. Once this is clear, now we are ready to take some questions. So now let's move on and see some numerical problem in order to solidify the concept that we recently learned. Now let's look into this question. It says that the medium 1 is air, and this is a second medium whose refractive index is √2, and we know that refractive index of air is 1. Okay, these are actually absolute refractive index. It says that the angle of incidence is 45 degree, very good, and the question says that you need to find the angle of refraction and also find the angle of deviation. So this is the thing that I haven't explained. I will explain it here while solving this question. So let's see, very easy. How to find angle of refraction from the concept that we have learned earlier. From here we can see that we have learned that refractive index in medium 1 into sine of angle that is formed in the medium 1, that is sine of 45 degree, is equal to refractive index in medium 2 and multiplied with sine of angle in the medium 2. So mu1 is 1, so 1 multiplied sine 45 is 1 by √2, mu2 is √2, and sine R we need to find out. Okay, so from here we can say that sine R is actually half, so half is equal to sine R, or we can say, therefore we can say that R is 30 degree. Very easy. So we got angle of refraction to be 30 degree. Now what is angle of deviation? You need to understand this. So let's see, angle of deviation is the angle by which the ray has deviated from its original position. Okay, so this white color should have been the original path of the light if there was no refraction, but due to refraction it bends towards the normal, and we got angle of refraction to be this one. Okay, this is the angle of refraction to be 30 degree as we have solved. Now angle of deviation is actually this, how much the path has deviated from its original path. So this is actually the angle of deviation. Now very easy, angle of deviation here is 45 degree, the original path that was making an angle 45 degree with the normal, but due to refraction it has bent away and now it is making angle 30 degree with the normal. Therefore the angle of deviation is 45 minus 30, so it's 15 degree. So we can say that it has bent 15 degree away from its original path. Therefore angle of deviation here is 15 degree. I hope the concept is clear. Okay, now let's move on to our next concept. Now we will look into a concept which says that what happens when the light rays enter a medium in such a way that the plane of entry is parallel to the plane of exit. As you can see that entry plane is parallel to exit plane. Now this is the plane through which the light is entering, and this is the plane through which the light is exiting out, and this is entering. Okay, we can see that both these planes are parallel, and we can see that the light is entering into the medium 2 and then exiting into the same medium, that is medium 1. So we can see that this is medium 1, this is medium 2, and then again it is coming back to medium 1. Let's see what is the concept that is embedded when this thing happens. Okay, this is very important. So the angle of incidence that the rays make in medium 1 is I, and the angle of refraction is given to be R. So let's see, we know from Snell's law that refractive index of the first medium into sine of I should be equal to refractive index of the second medium and sine of R. This is clear. Now if this is angle R, then this will also be angle R, isn't it? Because this and this are, we can see that this is normal and this is also normal. So this is normal, this is normal. These both normals are parallel, isn't it? So we have taken this as angle R. If you look into that figure, then if this is angle R, this has to be angle R, because these kind of angles are known as interior alternate angles. Interior alternate angles. So this is clear. So that angle will also be angle R, and this angle, that is the angle of coming out in the medium 1, is known as angle of emergence, because it is emerging out with that angle. Therefore we got for medium pair 1 and 2, we got this relationship. For the medium pair 2 and 1, okay, we will get refractive index of 2 sin R, because this is sin R. We are taking this and this medium now, okay, is equal to refractive index of medium 1, because this is actually medium 1, into sine of E. I hope this is clear. Now if you look into equation 1 and equation 2, we will see that mu to sin R and mu to sin R is common. Therefore if we compare this, we can say that if this and this are the same thing, therefore this and this has to be equal, isn't it? Because mu to sin R is equal to mu 1 sin I, and again mu to sin R is also mu 1 sin E. Therefore we can say that mu 1 sin I is equal to mu 1 sin E, or mu 1 got cancelled. Therefore we can say that angle I is equal to angle E. Therefore the angle of incidence will be equal to angle of emergence, and this will happen only when the entry plane, that is a plane of entry, and plane of exit is parallel. So this is very important. Whenever the entry plane and the exit plane is parallel, then we say that entering rays are parallel to exiting rays. Okay, why? Because you can see this angle of emergence is equal to angle of incidence. Therefore we can say that both the rays are parallel. So entering rays are parallel to exiting rays. Yes, it has deviated, and we will look into that by how much is the deviation or lateral displacement. We'll be looking into that while studying glass slab. Okay, so don't worry about that. As of now, just understand that whenever the entry plane and the exit plane are parallel, then the entry rays and the exiting rays will be parallel to each other. Okay, once this is clear, now let's move on to a little bit more complex situation. Now my question is, if there are three medium, like this is medium 1, this is medium 2, this is medium 3, and again this is medium 1, then what will happen? Again we will be using the same concept. Suppose this is angle of incidence, this is angle of emergence, this is angle of refraction, this is the first angle of refraction. If this is angle R1, then this has to be angle R1, interior alternate angles. If the incidence angle here is R1, then it will again refract and produce angle R2, okay, which will be different from R1 obviously. If this is R2, then this one has to be R2 again, because of interior alternate angle, and we have given this as angle of emergence E. So we'll be using the same concept again, that is mu 1 sin I. We are going from top to bottom. Okay, sin I is equal to mu 2 sin R1. Again if we go to the pair 2 and 3, we will see that mu 2 sin R1 is equal to mu 3 sin R2. Now if we look into third and first pair, then we will get mu 3 sin R2 is equal to mu 1 sin E, that is angle of emergence. So we got three equations. Now let's compare again. It's easy. Now mu 3 sin R2, mu 3 sin R2. Let me pick another color. Therefore we can say mu 2 sin R1 is equal to mu 1 sin E. Therefore we can write that mu 2 sin R1 is equal to mu 1 sin E. And if you look into the first equation, then we know that mu 2 sin R1, which is this one actually, is again equal to mu 1 sin I. So we can write this as, replace this as mu 1 sin I is equal to mu 1 sin E. Therefore mu 1 and mu 1 got cancelled. So we can see sin I is equal to sin E. Therefore, we can say that angle I is equal to angle E. Again, we can see that the angle of incidence is equal to angle of emergence. Why? Because the entry plane, if you look into this plane, entry plane is equal to exiting plane. Whenever the entry plane and the exiting plane are parallel to each other, then the rays entering and the rays exiting out are also parallel to each other. So this is the concept. Whether there are 3 number of mediums, whether 4, 5, 6, doesn't matter. Okay, so this is the concept that you need to remember. That we understood that the rays entering and the rays exiting out in these kind of situations are always parallel to each other. So once this is clear, now we'll be looking into our last problem and then we'll wrap up this video. Okay, now let's look into this question. It says that the angle of incidence is given to be 30 degree and it is asked to find out the angle of emergence. Okay, so simple. Just it's given that this is actually refractive index of air, and we know that refractive index of air is 1, and the refractive index of the circular body is given to be √3. Therefore, how to find out the angle of emergence? Very easy. We can use the concept given by Snell, that is mu1 sin I is equal to mu2 sin R. This is the angle of refraction. So mu1 is 1 multiplied sin I, that is sin 30 degree, is half, is equal to mu2 is √3, and sin R we don't know. Okay, now if you follow this path and then find out the value of sin R and you try to find out angle of refraction, then you'll see that you'll be landing into trouble. Okay, so without solving this, what we will do is we'll compare equation as we have done earlier. So let's see. So this is our first equation. We'll not solve anything. We'll just compare. For the second equation, we will be getting, in the first case, we have taken medium 1 and medium 2 as our pair. For the second case, what we'll be doing? Medium 2 and medium 1 as our pair here. So we'll be writing it that refractive index of 2 sine. Now what will be this angle of incidence? Now you need to understand the normal. This is actually the normal, and we know that normal over a circular shape always passes through the center of the circle. So this is the center of the circle is passing through that. So this is the normal. So you need to find out this angle. Now if you look into this figure, then it's very easy. We know that if this is the center, then the distance from the center towards the surface is actually the radius of the circle, and the distance from the center towards this surface is also radius. Therefore this side is equal to this side. Therefore this angle has to be equal to this angle as R. Okay, so this will also be sin R, which is equal to again mu1, because we are going to medium 1 again, sine of emergence angle. Easy. This is our second equation. Now if you compare this, it's very simple. You can see that mu2 sin R and mu2 sin R is common. Therefore we can say this is equal to this. So if you say mu1 sin I is equal to mu1 sin E, therefore mu1 got cancelled, and we can say that angle of incidence has to be equal to angle of emergence. Now angle of incidence is given to be 30 degree. Therefore angle of emergence will also be 30 degree here. Okay, but if you look into the concept, in the earlier case, we also said that if this is the ray of light entering into a slab of medium, then after refraction and while coming out, we saw that the angle of I was equal to angle of E, and we said that this ray is parallel to this ray. Okay, so that was the concept, and I said that it will be parallel and the angle of incidence will be equal to angle of emergence only when the plane of entry is parallel to plane of exit. Okay, and both the medium, that is the medium from which it is entering and the medium into which it is exiting out is same, then this concept will hold, that is angle I is equal to angle E, and both the rays will be parallel. But here we can see that this is a spherical body in which the plane of entry is not parallel to plane of exit. Okay, therefore we can see that the rays that is entering and the rays that is exiting are not parallel, but the angle of incidence is equal to angle of emergence in this case, but they are not parallel to each other as we have seen here. So this is what I want to say. I hope the concept is clear. I hope all the concepts that I have discussed are super easy and you have understood the concept as it should be understood. Okay, so this is all for this video. If you enjoyed this video, then please give it a thumbs up, and if you haven't subscribed to this channel, then please consider doing so. Till next time, enjoy your studies and build your concept, and I will catch you all in my next video. Bye bye.